We discussed about conductors and insulators earlier. There is another group known as semiconductors like germanium and silicon, which are bad conductors of electricity in their natural form. If some impurities like boron or antimony are added in minute quantities to these, they can have either an increase in free electrons or a deficiency of electrons. Then they become semiconductors. The process of adding impurities is known as doping. When there is a deficit of electron, it is called a p-type semiconductor. They have positively charged holes as charge carriers. N-type semiconductors, on the other hand, have excess electrons as charge carriers. Silicon has 4 electrons in the outermost shell. When it is doped with boron, having only 3 electrons in outer shell, it becomes a p-type semiconductor with deficit of electrons or holes. Doping with antimony, which has 5 electrons in the outer shell, makes it an N-type semiconductor with an excess of electrons. P-N junction is constituted by a combination of p-type and n-type semiconductors in a diode. Current flows across the junction only when the positive pole of the battery or voltage source is connected to the p-type semiconductor. This situation is known as forward bias. Positively charged holes are repelled by the positive terminal of the battery. Similarly, electrons are repelled by the negative terminal of the battery. They cross the junction and combine with each other. For this crossing to occur, there should be at least 0.7 volt for silicon junctions and 0.3 volt for germanium junctions. At lower voltages, there is a depletion zone of carriers at the junction. This causes a current to flow across the PN junction when it is forward biased. In the reverse bias situation, no current flows across the PN junction. That is how a semiconductor diode functions as a rectifier, converting alternate current into pulsating direct current as it cuts off one half of the AC. A diode is composed of a PN junction with p-type semiconductor on one side and n-type semiconductor on the other side, that is the PN junction. Then we have to know that when it is forward biased, there will be a depletion zone here where the current carriers will be minimal. And forward bias means p-type is anode that is connected to the positive pole of the battery, and cathode or the n-type is connected to the negative pole of the battery. This is the electronic symbol corresponding to the diode. Then this is the blown out picture of the diode. You can see that there is a ring at one end, or either a marker, which you can see here also, but this is a real diode. The marker is very tiny. If you are careful, you can see, or with when you see it directly, you can see very well. This is a rectifier diode, and this will be the cathode, and this will be the anode of the diode. So this basic information is needed. And when a diode is forward biased, these are silicon diodes. When silicon diodes are forward biased, there will be a voltage across, that is 0.7 volt. Usually for silicon diode, it will be 0.7 volt, and for germanium diodes, which are seldom seen nowadays, it will be 0.3 volts. So this is what we are going to measure using a multimeter, in the mode for diode testing mode. There is a selector switch which will select for diode testing. We have to know about the concept of peak inverse voltage, that is the maximum voltage which the diode will withstand in reverse bias condition. Usual diodes will withstand about 50 volt in reverse bias condition, but there are high voltage diodes also which can withstand very high voltages. So that is peak inverse voltage. When you apply an alternating current to the diode for rectification, you know that during one half of the alternating current, the diode will be forward biased, and during the other half of the alternating current cycle, it will be reverse biased. So that is where this peak inverse voltage comes in. If the peak inverse voltage is low and you are applying a higher voltage of alternating current to the diode, then it will break down. For testing a diode, you have to choose the selector switch in such a way that it indicates the diode symbol. That is how you test it. And then the black lead is connected to the cathode and the red lead is connected to the anode. Here I am using a yellow cable with crocodile clips on either sides to connect from the red lead to the anode, and you can see the display here 555, that is actually 0.555 volts or 555 millivolts, that is being shown here. Now we will reverse the connection and see. Now the connection of the diode has been reversed, and you can see that what is shown is 1. 1 in this multimeter means it is beyond the range. It is not measuring that. So that is because this is reverse biased now. When the diode is reverse biased, no current flows across the diode till it reaches the breakdown voltage or peak inverse voltage which we discussed in the beginning. Now I am testing another diode of the same type. You can see that there is slight difference in the voltage across the diode in forward bias condition. It is 538 millivolt rather than 555. This was the diode which we tested initially, and this is another diode. There is slight difference. Such variation can occur from device to device. Transistor is a semiconductor device invented by John Bardeen, Walter Brattain, and William Shockley in 1947, and they received the Nobel Prize in Physics for this invention in 1956. It is a device used to amplify and switch electrical signals. Large number of transistors can be included in a single chip known as an integrated circuit, which are the building blocks of modern computers and many other solid-state devices. Most of the transistors are currently made from silicon, while germanium was used earlier. Field effect transistors have only one kind of charge carrier, while bipolar junction transistors may have two kinds of charge carriers. In comparison to vacuum tubes, transistors are much smaller and require less power, often working at much lower voltages. Currently, two basic types of transistors in use are the field effect transistor (FET) and bipolar junction transistor (BJT). Terminals of the FET are named as gate, source and drain. Voltage given to the gate can control the current between source and drain in case of FET. Terminals of BJT are named base, collector and emitter. Current at the base terminal, which flows between the base and emitter, can control or switch a much larger current between the collector and emitter. That is how BJTs are used for amplification and switching. BJTs are generally grouped into two, NPN and PNP, depending on the types of semiconductors in them. N-type semiconductor has excess of electrons, while P-type semiconductor has a deficit of electrons or holes, which are considered as positive charge carriers and hence the name. These two types are made by mixing small amounts of other materials into the silicon chip by a process known as doping. There is difference in the amount of doping between various layers of NPN and PNP transistors. Emitter is heavily doped compared to other two layers. Collector is typically doped 10 times lighter than the base. FET is also sometimes called a unipolar transistor as they have only a single type of charge carriers. They can be N-channel or P-channel depending on the type of semiconductor used. They are named as field effect transistors as they use an electric field to control the current. Two types of FETs are the junction FET or JFET and metal oxide semiconductor FET or MOSFET. Voltage applied to the gate terminal controls the conductivity between the drain and source. Though Julius Edgar Lilienfeld proposed the concept of a field effect transistor in 1925, a working prototype could not be made then and had to wait for further development of semiconductor technology. Three main types of configurations in which transistors are used are the common emitter, common base and common collector. While two leads each are needed for input and output of an amplifier circuit, the transistor has only three. So one lead has to be common between input and output. The transistor configurations are named after the lead which is common to both input and output in the given configuration. In actual circuits, there will be resistors and capacitors in addition. Radio frequency circuits will have inductors and transformers as well. Values of each component will be calculated according to the purpose of the circuit. In all these configurations, the emitter is forward biased and the collector reverse biased. Most common type is common emitter configuration, in which emitter is grounded, base acts as the input and collector as the output. So the input is given between the base and the emitter, which is grounded. Current gain in this configuration, which is the ratio of collector current to the base current, is known as beta or HFE, which stands for hybrid parameter forward current gain common emitter. Beta is always more than 1. This configuration has medium input and output impedance levels. Both current and voltage gains are medium. There is a 180-degree phase change between input and output, so that output is the inverse of the input. In common base configuration, emitter is the input terminal and collector is the output terminal, while base is the common terminal. This configuration is also known as grounded base configuration. Alpha is the current gain in common base configuration. It is the ratio of collector current to emitter current. Alpha is always less than 1. When there is no AC input, the alpha is known as DC alpha. Low input impedance and high output impedance are features of common base configuration. Voltage gain is high, but current gain and overall power gain is low compared to other configurations. The input and output signals are in phase in common base configuration. Low input impedance can provide a good match to 50 ohms, which may be useful in RF linear amplifiers. Grounding of the base can also reduce unwanted feedback between input and output stages in RF circuits. Base is the input terminal in common collector configuration, also known as grounded collector configuration and emitter follower. It is called emitter follower because the emitter voltage follows that of the base, though the emitter voltage is lower by an amount equal to the turn-on voltage of the base emitter junction. Here output terminal is the emitter. Gamma is the current gain in common collector circuit. Though the current gain in this configuration is high, voltage gain is unity. Input and output signals are in phase. Emitter follower configuration has high input impedance and low output impedance. High input impedance is useful in preventing loading of the previous stage. Thus, it is an ideal buffer amplifier. Current gain or amplification occurs in transistors between the base and collector currents with common emitter configuration. It is technically termed as HFE, which stands for Hybrid Parameter Forward Current Gain Common Emitter. Another term is beta of the transistor. It is measured by dividing the collector current by the base current in a common emitter configuration. Most digital multimeters have an option to check the HFE of transistors. The transistor has to be inserted in the NPN or PNP slots according to the pinout diagram, and the selector knob turned to the HFE option to read the value on the digital display. Here you can see that BC547B, which is an NPN transistor, has been inserted in the socket for NPN transistors, and the selector knob has been turned to HFE on the dial. Digital display shows HFE value is 256, which is the current gain of this device as measured by the digital multimeter.